and we put it in particular places in the brain called acoustic windows, which I will touch on a little bit later. And again, ultrasounds, and in particular the transcranial Doppler, has a lot of important uses in the brain that can help us diagnose strokes, hemorrhages, sickle cell, and many various other cardiovascular brain disorders. My focus is actually on a different type of ultrasound. So there are three major types that I found in my research: the transcranial Doppler, which is more measurement-based, and then the focused and the unfocused ultrasounds. So these ultrasounds are more treatment-based. They focus on using the ultrasound energy to create a mechanical energy buildup in the brain to have different effects depending on the intensity and the amplitude of this ultrasound. So in-focus ultrasound in general, it can help replace surgical treatments such as those that typically are seen in Alzheimer's and various other diseases. And then unfocused ultrasound is more of like a stimulation type of, like a neurostimulation type of treatment. So this actually helps with patients with depression. We can help neuromodulate some of their neurotransmitters so that there's more release of dopamine due to the increased energy that the ultrasound is bringing. So I have a diagram down here that has like the three major uses for unfocused and focused ultrasound. So thermal ablation is a high intensity focused ultrasound. This can help with tumor removals. So it uses all of that energy and heat buildup to destroy the tumor that's located in the brain. We have the blood-brain barrier opening, which uses these focused ultrasounds to create so much energy inside of the blood-brain barrier that it actually inserts these microbubbles, which are tiny little pockets of air, into the blood-brain barrier to make spaces for medications to push through. And that's the focus of my research. And then again, neuromodulation is what I talked about with the depression and anxiety type of thing, where they more affect the neurotransmitters in the brain rather than the structure itself. So the acoustic windows that I mentioned a little bit earlier, these are defined to be the thinnest part of the skull, and it is located in four majorly common areas. There is the temporal region, which is right here where your temples are. There is the suboccipital, which is on the back of your neck here, shown in picture D. And then there is the orbital acoustic window, which is located actually right behind your eyes, where your skull kind of indents. And then the submandibular, which is right under your jaw, which you can see in figure B. There are some exceptions for who has an acoustic window and who doesn't. In my research, I found that interestingly, there was a lack of acoustic windows in Asian female populations. For a variety of different evolutionary reasons, they have developed a lack of particularly temporal acoustic windows, which impacts the way that they're able to get ultrasounds done, and it also impacts their eligibility for these ultrasound treatments. And before I get into all of the specifics of that portion, I want to quickly talk about the actual physics of the ultrasound. So most of the transcranial Doppler ultrasounds use something called the Doppler effect. It's in the name. So the Doppler effect is a physical phenomenon that affects all types of waves. So whether it's sound waves like the ultrasound or whether it's light, it occurs when the producer of a wave produces a wave that bounces off a moving object. So in this case, the moving object is our red blood cell. This is called an erythrocyte in most medicinal situations, but you can think of it as a red blood cell. And whenever the red blood cell is moving towards the transducer, it creates a higher frequency, which that transducer can then measure. And if it's moving away, then it creates a lower frequency. So this is seen often in traffic. So if you guys have ever been driving and then there's like an ambulance that passes by you, you hear it go like, that sound. So that happens because the sound waves, the frequency that's relative to you as a stagnant observer, as a still observer, and when the ambulance is moving, it's creating sound waves that when it's further away from you, it's lower, so it sounds like lower pitched. And then what's closer to you, it's creating sound waves that are getting pushed into smaller spaces, which sounds like a higher frequency. So physicians can use this phenomenon to help measure how quickly the blood is moving inside the brain to see how much these capillaries are either being blocked or if they're nice and open. The equation that these transducers use is modeled here, so it's derived from the original Doppler equation that was defined in the original textbook that it came from, and then it's derived to be slightly reordered in a different way. So FD in this case measures the Doppler shift, and then FS would be the original frequency that's being emitted by this transducer. FO is the received frequency that gets bounced back. C is the speed of the ultrasound wave, which was experimentally measured to be 1540. In most cases, it can range from about 1500 flat to about 1560. And then V is the velocity of the moving blood, which is what we're measuring. And then the 2 cosine theta is just to correct for the angle. So in most cases, the transducer will not be perfectly parallel to the blood vessel, which is ideal. The lesser the angle, the better. But in most cases, there is some angle, preferably less than 30, which is like the medically advised angle. And this can help us just kind of correct for that altered velocity that we get from bouncing at it, not from a straight line. So my project proposes using a COMSOL software to model the brain to figure out how we can make up for these acoustic windows that are lacking and help get a better idea of where these certain capillaries are, which areas of the brain we find the most like plaque buildup, which is the most common cause for Alzheimer's disease. So the COMSOL software can be seen here. This is a model of the brain that was in one of the studies that I was looking at. This is compared to a phantom brain, which essentially is just like a biological model, and then they also have a computer model, and it was the same. And then the COMSOL software actually uses the spatial Helmholtz equation and the finite element method for modeling the brain. My research itself did not go too deeply into this, but I do have this Helmholtz equation up here for reference. This is what they pushed into the software to make this brain model. So over here, you can see my ongoing investigation and also the efficiency of this mathematical model. So I'm proposing that we use the COMSOL modeling software to adapt the ultrasound technology for these altered head shapes, where it's harder to see these capillaries, it's harder to get the correct angle, it's harder to actually emit these ultrasound waves into these lackluster, if non-existent, acoustic windows. So here you can see the thicker the skull, the more attenuated this wave is. Attenuation is essentially when that ultrasound wave is getting absorbed or reflected, so it doesn't bounce back to the transducer. So it helps us understand the efficiency of that energy and how much we're actually getting back to measure that velocity, or to, of course, reduce those plaques that I was talking about previously. So hopefully my aim is to create a brain model that can help with these East Asian populations, help model their lack of acoustic windows in certain areas to see how we can alter our ultrasound intensity and our amplitude so that we can get through to those areas even without those traditional acoustic windows that have been used before. And this, I believe, will improve the efficiency for those with Alzheimer's that are also in populations that initially and currently aren't really eligible. So by doing this, I hope that more people will be eligible for this non-surgical treatment, because right now the only option for these people is to go and get surgery, which is very expensive, and it's very anxiety mongering for a lot of different people, especially those with lower English skills, which we do find in these female Asian populations. And thank you very much for your time.